So this video is meant to be a short demonstration tutorial of what used to be called sim mechanics, and now it's called Simscape Multibody, which is a toolbox for creating multibody simulations. So let me start the toolbox by, and that's within MATLAB. Um, Let me start the toolbox by typing Simscape into the command line of MATLAB. And this is Simscape, and we notice that it's got a bunch of different components, um, multi-body systems. But let me close that because we're going to talk about that in detail. It's got systems, it's got components that can be used in fluid simulations, for instance, hydraulics. Um, it's got a whole bunch of components that can be used in electrical simulations, simulation involving electrical components, for instance, electromechanical components, namely motors and such, semiconductors and converters, passive electrical elements, switches, etc. It's got components that could be used in simulations involving automotive systems, for instance, engines, transmissions, tires and vehicles, clutches, gears, brakes, etc. And of course, you can combine these components together and put together objects and simulations that involve all these components. But we are going to focus on Simscape Multibody. Um, so let's briefly go through its components, what components Simscape Multibody comprises. Um, so here are body elements. So for instance, a brick-like rigid body, a cuboidal object, a cylindrical object, ellipsoidal object. These are all rigid bodies. Or you can make solid objects through extrusion. In other words, you take some 2D shape and then extrude that 2D shape into a 3D shape by moving it along an axis. Or you can take a 2D shape and revolve it or rotate it about some axis of rotation and get a object of revolution. It's a spherical solid. It turns out this system also has ability to model some simple flexible objects, okay, flexible beams specifically. Okay, so those are all things that you can use to put together a multi-body system, right? Um, Now, of course, how do you put those objects together? You have joints, and you have a variety of different joints. Um, so let me zoom in a bit. So we've got a 6 degree of freedom joint, which means basically no joint between the object and the ground. In other words, it allows all degrees of freedom, all 6 degrees of freedom, this joint does. You can have a revolute joint, which is a single degree of freedom rotational joint between two rigid bodies. Okay, so this is the hinge joint, or it's a joint that we used in all our 2D simulations. It's the same as a door hinge. You can imagine a spherical joint, which is the same as a ball and socket joint. It's a 3 degree of freedom rotational joint. You can have a prismatic joint, which is a single degree of freedom linear translational joint, right? So if you have two rigid bodies, putting this prismatic joint between them allows for a single degree of freedom translation between the two rigid bodies. A cylindrical joint allows for 2 degrees of freedom, one a translation, another a rotation, right? So if you have two rigid bodies which have a cylindrical joint between them, then they can translate along some axis and also rotate along the same axis. And then we discussed universal joint, which is 2 degrees of freedom rotation, right? So yeah, so if you double click on any one of these things, you will see a description of the object and how exactly to define the object and so on. And it's got a bunch of different options that we can use to prescribe the various properties of the joint. And we shall see some of these things as we actually build systems involving these joints. Okay, a planar joint is basically planar sliding, and yeah. So I guess those are the primary kinds of joints that we might use. A bushing joint is a um, sort of a 3 degree of freedom joint, which maybe we'll discuss later on. In any case, those are all joints, and that's how you put together body elements. We can have constraints on different aspects of the model. Well, we can have gears and couplings. For instance, we can have belts and cables connecting different aspects of the system, right? Pulleys and so on. We can also have forces and torques, different types of forces and torques, contact force, spring and damper, external force that you yourself make up, some kind of an internal force, inverse square law force, etc. Right? Um, okay. So those are the main components of sim mechanics or Simscape Multibody. There's also this thing called utilities, which just has this one thing, which we shall use in just a moment. Um, we also have frames and transforms here. Let's double click on that. And by the way, this object I'm clicking, make sure that your full screen is used when displaying an object. So we have a variety of reference frames, rigid transformations, which is a rotation and a translation, and a world frame, which we can use, which we will use in a minute. That's it, I suppose. Okay. Okay, so now that we've seen all the stuff, let me move these things. And actually, let me close all the stuff for now, and then try to create a simple pendulum simulation in Simscape Multibody. Okay, so I already actually created one right here, and we can run it if we want, but this is a simple pendulum with a 200 Newton meter torque. Um, so we can run this and let's see, get a simulation that looks like this. It's oscillating, but it's oscillating about some weird angle because there's a 200 Newton meter torque acting on this axis. And because of that torque, it's not oscillating about the vertical downward, but it's oscillating about some axis that is determined by this number 200. Okay, so that's a simple pendulum simulation. Now let's see how to build that from scratch. Okay, so we're just going to build that from scratch. To build that from scratch, you would just go Simscape and then go New Blank Model. So it creates a completely blank model, nothing in it, right? So we don't have anything in it. And all Simscape, and then let's save it actually. Let's save it as simple pendulum new or something. Okay. And all these, so it's completely blank still. All these Simscape Multibody simulation models need to have three main components. So let me just drag and drop those things. The first thing is in the Simscape Multibody utilities. It's called mechanism configuration. Fancy name for something really simple. What I'm doing here is just copying, Control C or Command C. Command C if you're on a Mac, Control C if you're on a PC, and paste it here, Control P or Command P. And we can double click this to see what's in it. And all it's specifying is the gravitational constant. It specifies uniform gravity, the value of the gravity in some global Earth fixed frame. And then if we are ever going to use this model for analysis that involves linearization, then this is the delta parameter for linearization. In any case, it's not super important right now. but all for the purposes of this simulation, all it does is specify gravity. So we are actually going to do a 2D simulation where z is perpendicular to the plane and y is the vertical direction. So I'm actually going to say gravity is in the negative y direction, and it's about 9.8. Uh, and the z direction has no gravity. There's just gravity in the y direction, no gravity in the x direction. Okay, so that's the mechanism configuration. And then we're going to drag and drop the world frame. So copy, paste. So we're going to define the world frame, which is the frame relative to which everything else is um, referred to. And uh, so mechanics, I believe, assumes that the world frame is the so-called inertial frame, right? So it's inertial. And then that's a component for all some mechanics models. And finally, let's look at sim mechanics utilities. So utilities under sim mechanics, I'm double clicking that. And there is this thing called solver configuration. Copy, paste. So we just dragged and dropped three things into the blank file. You can save this thing so far. And all these things are pretty much mandatory. Um, this is the mechanism configuration defining gravity, world frame, nothing to it. That's just the world frame, okay. And then the solver configuration defines things like how accurately do we want the simulation to run and so on. So for now, let's just ignore this, but it just needs to be there. Okay, so and then we can connect all these things together. The way to connect them, MATLAB says, is click on this and then click on this. It makes a connection. And then we can drag this here, right? So click, drag, and connect. Okay, so those three things have been connected. And there's nothing else in the system. So if we actually run, nothing happens. It does a run of 10 seconds, but there's nothing in the system, so it just does this blank simulation. Okay, now let's put in a rigid body into the system. Okay, so let me close this thing. Let's double click on Simscape Multibody and double click body. And let's just make a simple pendulum out of these brick solids or cylindrical solids, doesn't matter. But let's do it with brick solids. I'm going to copy and paste it. And we can double click it. It looks like a cube, 1 meter cube. I'm going to change the dimensions of this object and change it to 1 meter long, 0.1 meter wide, 0.1 meter tall. Okay, then I go apply. Then it says parameter values may have changed. Press F5 to update this visualization. I actually do not know how to press F5 on my computer, so I'm not going to do that. But if you click on this, it actually updates the visualization as well. And that's what the new object looks like, okay? And this, by the way, is the world frame. And inertia currently is being calculated from geometry. So inertia properties are being calculated from the geometry of this object and assuming that the density of this object is 1,000 kilograms per meter cube, basically water. If we make it 8,000, it becomes steel, roughly. And we can see what the mass and inertia properties are based on this density and this volume. Update. Mass is 80 kilograms. Center of mass is at 0, 0, 0 in its own frame. Moments of inertia is known here. These are the principal moments of inertia. And then finally, we have those are the principal moments of inertia along the ixx, iyy, izz, because the object is basically the same in the y direction and the z direction. Ixx, iyy, and izz are the same, but ixx is small because that's the long axis, right? Moment of inertia is small about the long axis, but then it's equal about these two axes. Okay, products of inertia, basically the off-diagonal elements, they're all zero. We can change the visual properties as well. Let's make it some color like that. So if we wanted to update it, we can either close it and open it again or just keep it closed. Anyway, that's the object. We can make it slightly transparent, which is helpful. Right, so it's slightly transparent, or we can make it less transparent. Okay, transparent objects are helpful in these simulations because they can see, it allows us to see what goes on behind the object. Okay, so that's a brick. We can connect that brick or pendulum to this world frame, save, and then run. And it looks like nothing happens, right? Because we've essentially, this connection is a rigid connection between this, specifically the center of mass of this object and the world frame, actually. So nothing happens. So if we say brick frame, um, this is the so-called Mechanics Explorer. If you click on the brick frame, it's got this body fixed frame, and it just sits there. Nothing happens, okay? Because the object is rigidly attached to the world frame right now. Now, what we want to do is attach this point to the origin of the world frame. Okay, so we want to attach this point to the origin of the world frame. What is this point? How do we say this point? So there's a body fixed frame here. This is the x-axis, the long axis. In the x-axis, this point is going to be minus 0.500, right? Because the length of this object is 1. This point is going to be minus 0.5 and then 0, 0, because we want to say y and 0, 0. We are going to attach the center of that square, cross-sectional square, to a, say, pin joint or a revolute joint. Okay, so this whole thing is 1. This is 0, 0, 0 in the body fixed frame, because that's where the body fixed frame is. This point is going to be minus 0.500. Okay, so to get an access to this point, what we're going to do is first delete this thing. Okay, delete that. And I'm going to type Command R or Control R to rotate this so that it's just more convenient to attach something to the bottom of it. Okay, save. And then what I'm going to do is use what's called a rigid transform. So copy, paste, and then I'm going to rotate this using Control R or Command R as well, so that I can attach the output of this to this. Okay, so what have we done? We've attached basically the center of mass of the brick, the origin of the body fixed frame of the brick, to this B port in this rigid transform module. Okay, let's double click on the rigid transform, see what it says. It says defines the fixed 3D rigid transformation, fixed, important word, 3D rigid transformation between two frames. Okay, and in this case, they are defining frames as containing both a translation and a rotation, in other words, an origin as well as the directions of the unit vectors. And it says Two components independently specify the translational and rotational parts of the transformation. Ports B and F are frame ports that represent the base frame and the follower frames, respectively. The transformation represents the follower frame origin and axis orientation in the base frame. Okay, so what we're going to do, so if we connect the base frame B to um, basically the body fixed frame of the brick solid, the base frame becomes the body fixed frame. And then what we want is a follower frame that is shifted by 0.5, negative 0.5 along the x-axis. Okay, so what I'm going to do is rotation none, translation, standard axis, which I think means the current local axis, and minus x. If you can do minus x or plus x, if you do plus x, we do an offset of minus 0.5 and then go apply. Okay, and then connect this rigid transform to the wall frame. Okay, so what we have done is, this is the body. It's got a body fixed reference frame at its center of mass, and then we've used this rigid transform and created a new axis, new coordinate axis that is offset by minus 0.5 meters along the x-axis. So let's actually run this to see what it looks like. Okay, it looks exactly the same. Nothing happens. But let's actually click on the brick solid. It still shows this body fixed frame. But then let's click on rigid transform. It actually shows these two frames. So this is what we just created, the rigid transform. This is the base frame of the rigid transform, right? So the base frame of the rigid transform is attached exactly to the body fixed frame. So this is where the base frame is. And then F, the follower frame of the rigid transform, is here. Okay, it's minus 0.5 along the x-axis of this base frame. Okay, so we just created this new frame. Now we have access to this point and the axes at this point. Okay, but of course, when we run this thing, nothing happens because, well, it's still rigidly attached to the wall frame. Okay, still rigidly attached. So what we're going to do is put in a joint that actually allows a degree of freedom or two. So let's go to joints and create or add a revolute joint, which is a single degree of freedom rotational joint. Let's put that in here. And then before we click on these things, let's double click this and see what it says. Represents a revolute joint acting between two frames. This joint has one rotational degree of freedom represented by one revolute primitive. The joint constrains the origins of the two frames. So this has a frame of its own, namely, basically, this allows a relative rotation between the base frame and the follower frame of the revolute joint. Right? The revolute joint has a base frame and a follower frame. It allows a relative rotation between these two frames, and it says that the joint constrains the origins. The base frame and the follower frame has the same origin, and it constrains the z-axis of the base and follower to be coincident. So the base frame z-axis is the same as the follower frame z-axis, and then it says the follower x and y-axis can rotate about the z-axis, right? So basically the follower rotates about the z-axis of the base frame. So it's basically a z rotation. So let's connect the base frame of the revolute joint to the wall frame, which means that the base frame becomes basically the wall frame for this revolute joint. So what that means is that our rotations of this revolute joint, rotations enabled by this revolute joint, will be along the z-axis of the world frame. Recall that the z-axis of the world frame is perpendicular to the plane. So that's exactly what we want. We want a rotation about the z-axis. perpendicular to the plane, EZ, E sub Z. Okay, so we've just made the base frame of this revolute joint same as the world axis, and then we make the follower of this revolute joint the same as this follower. Okay, and then we just saved it. So what have we done? We've taken this, defined this rigid body, gotten access to a point that is at the end of the rigid body, connected the end of that rigid body to this revolute joint, and then connected the revolute joint to the world frame. Okay, now let's run it. And we see that it actually oscillates. We can zoom out a little bit and maybe pan so that this is the center. Okay, and we can run this again. So we did everything right and it just oscillates. So that's a simple pendulum simulation. Okay. I believe right now when I click play here, it is just um, doing the animation over and over again. But then when you run this, it reruns the whole simulation and then does the animation. In other words, solves the differential equations and then does the animation. But then once it's done the animation once, when you click this, it just stores, runs the stored animation, or replays the animation, or remakes the animation, but without necessarily solving the differential equations. You can slow down the animation a little bit if you want, or speed up the animation. Like so. Okay, so that's a simple pendulum simulation. Um, so it took a while. So it's not, it doesn't take, it takes a few minutes to create this animation or simulation. Notice that we didn't do a couple of things that we were supposed to do for doing a simulation like this. We didn't yet define initial conditions for the system. How do we do that? It looks like it just assumes some default initial conditions. Um, so to actually do that, you have to, the initial conditions are specified using the joints. Um, so we double click on the revolute joint. It's got a bunch of different things here. So let me just minimize all these things. What's called the state targets is actually the initial conditions for the angle degree of freedom supported by, enabled by this revolute joint. If we say specify position target, specify velocity target, it will allow you to give you the value of the initial angle and initial angular velocity. It looks like you can specify that in degrees or radians. Looks like by default it's assuming 0 everywhere. So that's why it started out flat, horizontal, and then presumably that's 0 because it makes sense based on our conventions. Okay, so let's make it pi by 4 or something. And then velocity target is still 0, let's say. Or maybe let's make it like very small positive. Pi by 4 radians, not degrees. And this is also radians per second, let's say. And then we apply. Then we go OK. Then save. Then run. So now we have a new simulation. It's already started running, but let me click on this so that the whole thing is can be viewed, and then let me pan it and then zoom out maybe. Zoomed out a little bit. So what that allows us to do, let me actually run the simulation animation again. So it starts from there, right? So we gave an initial angle of pi by 4 or 45 degrees. So it starts out at 45 degrees to this uh, basically x-axis, and it goes like that. If we had specified a bigger um, initial velocity, we could have uh, um, potentially seen it maybe move up a little bit initially and then go back down. Let's see if that works. Okay, so I guess barely it moved up and then came back down. Okay, so that's basically a simple pendulum simulation. And then in the next video, we will see a double pendulum simulation, and then uh, uh, maybe see how to add torques to this simulation.